In this video, you'll learn the basic components of the spine-ue4 runtime and how to play animations and manipulate your skeleton using blueprints or C++ code. You can explore all the components provided by the spine-ue4 runtime by selecting an actor and clicking on the Add button in the Details panel, then type Spine in the search field. To make a skeleton into an actor, you can use either the skeleton component or the skeleton animation component. These components reference skeleton data and an atlas, which they can use to animate and render the skeleton. In general, you'll want to use the skeletal animation component because it allows you to more easily apply animations to your skeleton. This component is based on the skeleton component and hence inherits all the skeleton component's features. The skeleton component can be used as a base for your own custom components. The skeleton renderer component is responsible for drawing the current state of a skeleton or skeleton animation component on the same actor. This component relies on the texture atlas asset referenced by the skeleton or skeleton animation component to locate the necessary textures for rendering the attachments of the skeleton. Let's animate a skeleton using the skeleton animation component in Blueprints. We will start with the skeleton already placed in the level. If you're unfamiliar with importing and placing skeletons in a level, please refer to the previous video titled Getting Started with Spine-ue4. Create a new blueprint by pressing the Blueprint button next to the Add button in the Details panel, and then press Select with default settings. Switch to the Event Graph tab. Right-click within the graph area and input Set Animation in the search field. Then select the Set Animation node. This will add a Set Animation node with the Spine Skeleton Animation component connected to the target pin. To set an animation, specify the index of the track where you want the animation to be queued, the animation's name, and whether the animation should loop. Connect the execution pin to Event Begin Play. Then compile and play the level. You'll see your skeleton plays the specified animation. If no animation is played, check to see if the animation name you entered is correct. You can verify the correct animation name by expanding the animation section of the skeleton data asset details for that skeleton. To prevent errors, you can click each animation name to select it and press Ctrl+C to copy and paste it into the animation name property. Next, let's delve into animating skeletons using C++ in Unreal Engine. We'll start by examining the example project bundled with the spine-ue4 runtime, specifically the example levels located in the Getting Started folder. Open the first level titled O1-Basic-Animation. This level provides a demonstration of how to manipulate a skeleton animation component through C++ code. In the Outliner panel, open SpineBoy CPP pawn. This will open both the header file and the source file. Focus on the source file named SpineBoy CPP pawn.cpp. Here, Spine Skeletal Animation Component.h is included. In the Begin Play method, the Spine Skeleton Animation Component is found and stored in the Animation Component variable. Then the Set Animation method of the Spine Skeleton Animation Component is called to set the walk animation for track 0 with the loop parameter set to true. In the Tick method, the Spine Skeleton Animation Component is again located and stored in the Animation Component variable. The animation state is then obtained using the getAnimationState method, storing it in the state variable. Now the TrackEntry object of the current animation on track 0 is obtained using the getCurrent method, which is stored in the entry variable. If track 0 has a track entry, the script extracts the animation name through the getAnimation and getName methods. This name is then added to an on-screen debug message. When playing the level, you'll see SpineBoy executing the walk animation as specified in the C++ code. Additionally, the debug message on the screen will display the name of the currently active animation. Feel free to modify this script and experiment. Remember to click the Compile button after making changes to ensure your changes are applied. Now let's explore the more complex level titled O2-complex-animation. Here we will explore queuing multiple animations and manipulating the skeleton's orientation. As you play the level, you'll see that Spine-Boy first flips to the left, followed by a 3-second walk animation. Afterwards, it transitions to a run animation and after another 3 seconds, changes to an idle animation. Let's open the event graph of spine-boy_blueprint to see how this is done. In the first comment box, a setScaleX node is connected to event begin play. Its ScaleX value is set to -1, so the skeleton is flipped when the level is started. Here we can also see that the walk animation is set as the first animation to be played. Moving to the second comment box, the run animation is queued on the same track as the walk animation using the add_animation node. This node inherits the properties of the setAnimation node, along with an additional parameter named delay. Here, delay is set to 3 seconds, so the walk animation starts and then switches to the run animation 3 seconds later. The animation will transition smoothly because the default mix time is defined in the Spine-Boy data asset. In the third comment box, the idle animation is queued on the same track with delay set to 3. So 3 seconds after the run animation starts playing, the idle animation will be mixed in. When delay is positive, it designates the time from the start of the previous animation to when the queued animation starts. When the delay is 0, which is most common, the queued animation will start mixing in so that it completes the mix when the previous animation has finished. For example, if you added the idle animation with a delay of 0 and a mix duration of 0.2, the mix starts 0.2 seconds before the playback of the run animation is completed. When a negative value is set, the animation starts that much before the previous animation's duration. If we set the idle animation's delay to -0.2 seconds, the idle animation activates 0.2 seconds before the completion of the previous animation. setAnimation and add_animation each return a TrackEntry object. We have already seen the C++ code example to get the current animation name from the TrackEntry object. There are many other uses for TrackEntry, such as responding to specific animation events or customizing the playback of that specific animation. For example, if you drag from the return value pin of the setAnimation node and add a setTimescale node where you connect the execution pin to the add_animation node, only the walk animation will be played at the speed set by timescale, and the subsequent run and idle animations will play at normal speed. A list of actions that use a TrackEntry object can be seen by dragging from the return value pin and typing TrackEntry in the search field. The multiple tracks and events level demonstrates how to use multiple tracks to play 2 animations simultaneously and how to react to animation events. When playing the level, you will see the raptor simultaneously playing the walk animation and the animation of grabbing the gun and putting it back in the holster. You'll also hear footstep sounds when the raptor's feet touch the ground. Let's take a look at the event graph of raptor_blueprint. In the first comment box, a setAnimation node is connected to event begin play, where the walk animation is set on track 0 with loop active. In the second comment box, the TrackEntry object returned by setAnimation is bound to the custom event via the bind event to animation event node. When we get a user-defined event called footstep, it passes through the true print of the branch node and plays back the footstep sound. User-defined events can be defined in the spine editor, where they can be added as keys in your animations. Beside the event name, each event key can have integer, float, and string values that can be used at runtime for various purposes. For example, you can adjust the sound volume using the float value of the event key. In the third comment box, animations gun grab and gun holster are queued on track 1. The gun holster animation is added with delay set to 2, which means the gun holster animation will play 2 seconds after the gun grab animation starts playing. The gun grab animation is less than 2 seconds long, but the last pose of the animation will be kept until another animation is applied to the track or if the animation is mixed out to an empty animation. This means Spine-Boy will hold his gun until the gun holster animation starts playing. The two animations are looped by binding to the complete event of the TrackEntry object returned by addAnimation. So far, we have explored binding to the delegate for TrackEntry Events. You can also bind to the delegate for AnimationState Events. This allows you to listen to all animation events played by that animation state. You can locate the list of events that can be bound in the Events section of the Details panel when a skeletal animation component is selected. Click on the plus sign of each event to bind to an AnimationState event. For example, you can use the Start event of AnimationState to display the name of the animation that began playing on track 1. Drag from the execution pin of the AnimationStart node and then select the getCurrent node to connect it. Set the track index of the added getCurrent node to 1, then drag from the execution pin and choose the getAnimationName node to connect it. Connect the return value pin of the getCurrent node to the target pin of the getAnimationName node. Drag from the execution pin of the getAnimationName node and choose the printString node to connect it. Then connect return value to endString. When playing the level, the animation name will appear in the upper left corner of the screen when a new animation starts playing on track 1. To bind a TrackEntry delegate, drag from the return value pin and enter TrackEntry into the search field. Then choose one of the actions where the name starts with Assign Animation based on your specific needs. When adding the chosen event node, a Bind Event To node is automatically added. For further information on each event, please refer to the documentation. The basic controls level demonstrates how to animate a skeleton using player input. When playing the level, you will see that pressing the H or K key will cause SpineBoy to play the run animation, facing to the left or right. Pressing the space key will fire his gun. Let's examine the event graph of controlled SpineBoy_blueprint. In the first comment box, an enable input node is connected to event begin play, and a get player controller node is connected to the player controller pin of the enable input node. This configuration allows us to bind actions for various input events. The idle animation is then set on track 0 as the first animation. In the second comment box, actions are defined for the H key. When pressed, SpineBoy's scale X is set to -1 to make SpineBoy face left and run on track 0. When releasing the H key, he returns to idle. In the third comment box, actions are defined for the K key. These actions are the same as for the H key, except the scale X value is set to a positive value. In the fourth comment box, actions for the space key are defined. When pressed, the shoot animation is set on track 1 with a loop set to true. When released, an empty animation is set on track 1, allowing the shoot animation to be mixed out over 0.2 seconds. As previously mentioned, even if the animation has ended, the last pose will be retained until another animation is queued or an empty animation is set on the track. The Set Empty Animation node serves to reset track 1 to empty. The Driving Bones level demonstrates how to use the Spine Bone Driver component to transfer the transforms of an actor to a skeleton bone, and how to move the bone via the bone driver. This is controlled by moving the actor via keyboard input. When playing the level, pressing the U, H, J or K keys will move the hover controller bone. In the event graph of spine_hover_blueprint, a set animation node is connected to event begin play, and the hoverboard animation is set on track 0 with loop enabled. This sets the foundation for SpineBoy's hoverboard movement. The Spine Bone Driver component is attached to hover_controller_blueprint. You can drive a bone by specifying the actor and the target bone name, then choosing which of the actor's position, rotation or scale properties will be used to modify the bone. If you change the location of this actor, you'll notice that SpineBoy's hoverboard moves along with it. However, it's essential to know that the transform of the Spine Bone Driver component won't affect the bone if the Use Component transform is set to false. The direction of the tip remains fixed even when the hoverboard controller bone is moved. This happens because an IK constraint ensures it always points towards the board-IK bone. Now let's explore the event graph of hovercontroller_blueprint. On each tick, check to see if there was a key input from the U, J, K, or H keys. If any of these keys are detected, the value of the vector corresponding to the current actor's location is adjusted with the Add World Offset node. This allows you to change the location of hovercontroller_blueprint, thereby affecting the transforms of the hoverboard-controller bone through the spine bone driver component. The bone follower level demonstrates how to use the bone follower component to make an actor follow a skeleton bone. You can see how this works within Raptor_blueprint, where the bone follower component is attached. In the target property, spineboy_blueprint is specified and the front-fist bone is chosen in the bone name property. The actor with the bone follower component then follows the position, rotation, and scale of the target bone. Here we only have use position enabled, so rotation and scale of the target bone will be ignored. This allows another skeleton or another object, such as a particle system, to follow a skeleton bone. The following behavior can be disabled by setting the use component transform to true. Additionally, bone follower_blueprint facilitates switching the use component transform property with a simple left click or by pressing the space key. The skins level demonstrates how to change skins on a skeleton. Initially, before playing the level, you'll see the girl skin in the viewport, but when you play the level, the boy skin appears. You can toggle between the boy and girl skins by left-clicking your mouse or by pressing the space key. Let's take a closer look at the event graph within the Set Skin blueprint. In the first comment box, a Set Skin node is connected to Event Begin Play, which sets the boy skin on the skeleton. Then the walk animation is set on track 0 with loop enabled and player input is enabled. In the second comment box, actions are defined for toggling skins. When the left mouse button or the space key is pressed, the boy skin is set if the local variable isGirl is set to true. Conversely, when isGirl is false, the girl skin is applied and isGirl is set to true. The set skin node can only be used for a single skin, so if you want to set multiple skins on your skeleton, use the set skins node. The skin names pin of the set skins node assumes a string type array, so create an array with the names of the skins you want to combine, then connect it to the skin names pin. Note that when setting another skin on a skeleton that already has the skin set, the set slots to setup pose function must be called after the skin is set. If you do not call it, the previous skin may remain partially in place. The UMG UI level demonstrates how to integrate the spine widget into your UMG UI. This allows you to have a skeleton remain in a fixed position on the screen even when the camera moves. When playing the level, you will see the raptor skeleton stays in the same position. Let's see the level blueprint, which can be opened by selecting Open Level Blueprint from the Blueprint button on the main toolbar. The UMG Raptor widget blueprint is added to the viewport here. You can select the UMG Raptor widget blueprint in the content drawer from the magnifying glass sign. Double-click to open it. Select the Raptor widget in the Visual Designer. You can see that almost the same properties as the skeletal animation component are displayed in the Details panel. This widget has the same interface as the skeleton animation component and is compatible with both Blueprint and C++ code. To add a spine skeleton to the UMG UI, click and drag Spine widget in the Spine section of the palette panel into the viewport or into the hierarchy where you want to add it. Next, set the Atlas and Skeleton data asset on the Spine widget. Resize it in the Designer viewport to fit your requirements. The skeleton will resize automatically while keeping its aspect ratio and fill as much space within the widget as possible. Switching from Designer mode to Graph mode allows you to modify the blueprint of the widget. In UMG Raptor's event graph, a set animation node is connected to event construct. It sets the walk animation on track 0 with loop enabled. For the skeleton animation component, this is all that is needed to play the animation. But for the spine widget, we also need to connect to the tick event with the widget's tick function. Otherwise, the animation will not be played. Now you have learned about the components and major functions provided by the spine-ue4 runtime. If there is anything you would like to know more about, please refer to the spine-ue4 runtime documentation. Besides the examples and documentation, more information can be found on the Spine forum where you can post your questions if anything still remains unclear. I hope this video has been helpful and thank you for watching.